Hello, statisticians. Now we're going to look at the significance testing for the slope of the least squares regression line. So we're going to use our typical testing protocol for that. And the parameter is going to be beta. So we use the Greek letter beta to represent the population slope of this least squares regression line. So if we took the entire population, plotted their x and y, and did a regression on it, we would get beta as the slope. So we're not going to do anything with the y-intercept. We're just going to do the slope in this situation. And it's important to say that it's the regression line relating the y variable to the x variable when you make that statement. So we can test against any claimed value of b. But most of the time, we're going to claim that b is equal to 0. So we want to kind of tell whether there is a linear relationship, whether x can predict y. So is there a multiplier that we can multiply to the x value to kind of turn it into a y value that we can then add the y-intercept to and use it to predict the y value? So we're trying to see if x is affecting y. If x doesn't affect y, then essentially y just stays the y-intercept the entire time. The equation just becomes y equals a as opposed to, or the y-intercept, as opposed to y equals a plus bx. So we're trying to see if there's a correlation between the x variable and the y variable. The alternative then, it can be one-sided or two-sided, but if we can say that it's not 0, then we can say that it does, that x does predict y in some way. It doesn't cause a change in y. We have to be careful there, but it can be used to predict. It does correlate to y values. So the assumptions for the confidence intervals are going to get used again for these tests. So L means it has to be a relationship has to be linear. Independence have to be, or observation have to be independent, just like always. The distribution of the response variable has to be approximately normal for every value of the explanatory variable. So there's that picture in the book with that regression line sitting there, and then those nice normal curves that are kind of raised up out of the book. I can always see that picture in my head. In your book, if you're wondering which one that is, that's in the Practice of Statistics edition 4, and it's back in the confidence intervals piece. It is on page 742. It's really a neat picture. But we don't want to test every value of the explanatory, every x value, and check to see, gather all the y's together and see if they make a normal distribution. So what we do instead is we look at the residuals. And the residuals then, they will all, if all the y's are normal at each value, so some of the y's are above the regression line, some are below, but they most kind of mound up at the regression line, then those residuals should be about normal as well, with kind of the most common residual is 0 or close to 0, and the least common ones further away. So if we make a histogram of the residuals, it should be approximately normal. Or if we make a stem and leaf plot, or if we make a normal probability plot, we should get a line in that situation. The dot should kind of fall on a line. E is equal variance, so that means that the cloud of the residuals on the residual plot, that should just kind of be the same thickness all the way across for every value of x. It shouldn't get bigger or smaller. And then R is that it was produced by some random sampling. So if it's an observational study, it has to be a random sample. And if it's a experiment, there has to be randomization to treatments. We a lot of times call that S. In our other ones, it was SIN, so sample well. So that's essentially what we're doing here. We're sampling well or experimenting well. So you could call this lines if you wanted to instead of liner. And then we're going to name the test. This test is a t-test for the slope of the regression line. So there's no one sample, two sample, nothing like that. It's a t-test for the slope of the regression line. Then we have to make our test statistics. So we're going to take a sample. We're going to do a linear regression. We're going to find our slope. We're going to subtract off the hypothesized slope, and we're going to divide by the standard error, because remember, those b's, all those sample slopes, form a sampling distribution that is normalish if all those conditions were met. The standard error is how variable those b's are, how different the b's are from the different samples. To calculate the standard error of the b's, That's the standard error of the residuals divided by the standard deviation of x times the square root of n minus 1. Then we got to get a p-value. So from that sampling distribution that we know is approximately normal and kind of, we're going to call it a t distribution. We're going to map it to a t distribution. We then can get the probability in the tail from that, and we can link that to a p-value. The t distribution that's going to match up with our sampling distribution of b is going to have n minus 2 degrees of freedom. And if it's a two-tailed test, so if we do a not equal to 0 or something like that, then we have to double the probability to get the p-value. If you see Minitab output, oftentimes that is a two-tailed p-value. So if you only want a one-tail, then you have to divide the p-value by 2. Then we got to compare it to alpha. If the p-value is less than alpha, we reject it. Because remember, alpha is our appetite for, or courage factor. We're okay being wrong 5% of the time or 10% of the time or only 1% of the time. The p-value tells us kind of the probability that we're wrong, given that HO is correct. If p-value is greater than alpha, we fail to reject the null hypothesis. So when we make our conclusion, we have to make sure that we restate the relationship that we're trying to fit the linear model to. So in context, figuring out what's going on, state whether we have enough evidence to suggest that the slope of the line fits HA or not. So we have enough evidence to suggest that the slope is not 0 or is greater than 3.2 or something like that. Or we don't have enough evidence to say that it's not 0 or that it's not greater than 3.2. If it's a two-tailed test, if it's a two-tailed test against beta equals 0, it's good to say that the correlation exists. So a two-tailed test says 0. Even if we have a big slope, and I have students that say that, oh, this is a really big slope, so it really affects it a lot. It doesn't mean that it causes any kind of change. The size of the slope really doesn't matter. Even as far as causational goes, the R value, even how tightly packed the numbers are, or the actual data is to the regression line, that doesn't tell us about causation either. Remember, the only way to establish causation is to do an experiment instead of do an observational study. So here's an example from page 61, number 14 in your book, or 761, 14 in your book. They did some studies here to see if the amount of time that a toddler spends at the lunch table affects the calories. Affects. The remain at the lunch table help predict how much they eat, how many calories they eat. So time is the average number of minutes they spent at the table when lunch was served over several days. I've got some typos there. And calories is the average amount or number of calories that the child consumed during lunch. Here's the data that they collected. They collected it from 20 toddlers. So we're going to let beta represent the slope of the population regression line. So if you did all the toddlers in the world, relating average calories consumed by a toddler at lunch and their average time they spend at the lunch table. Research question asks whether times helps predicts the calories. So here our null hypothesis is that beta is equal to 0, meaning that it doesn't help predict calories. The alternative is that it's not equal to 0, meaning that we can use it to help predict calories. Okay, let's check the assumptions for this one. So you got to reference the scatter plot here. If it's provided, reference it. If it's not provided, you have to make sure you label your axes. So there's the scatter plot. We would say this scatter plot shows no distinct curvature, so it suggests a linear relationship. Also, then we look at the residual plot, and the residual plot gives us, there's no pattern to it. So that also suggests a linear relationship. So you want to check both of those. Independent, so as long as the toddlers weren't next to each other at lunch and affecting how long each other ate and stealing, and one gets up, that makes the other one get up and everything. As long as the observations were correct, there's probably more than 200 toddlers in the world because we probably sampled no replacements. So that's that 10% rule. So now we have to look, this is that normal condition. We have to look at the residuals. So I made a stem plot of the residuals. There's no obvious skew. It's mound shaped, so it's pretty good, approximately normal distribution. So that tells us that the y values are approximately normally distributed at each x value. Equal variance. So looking at that residual plot again, it's kind of that there's, let's see where that pattern go. There we go. The residual plot is right there. You can see that it doesn't widen out or anything like that. It just kind of goes along. It's about the same distance away the whole time. Just goes like that. Alert would be like if it started to go like this and like this, that would be bad news. Okay. So here, evidence according to the residual plot, the variability of residuals is approximately equal across all values of x, and then random again, or sample well, the data is from a random sample of toddlers. All right. So now we're ready. The conditions are met for a t-test on the slope of the regression on the regression line. Alpha is equal to 0.05. I just chose that. Now we have to get our test statistics. So we're going to run a linear regression on our sample, the sample that they gave us, and we need to get our b value for that. So if it's not given to you, then you kind of do this. You put your x's in L1, you put your y's in L2, you run the lin-reg t-test, and that's going to give you your regression equation. It's going to give you the standard deviation of the residuals. It's going to give you the t value. It's going to give you the p value. And most of if you have a stat wizard, you get to pick whether it's not, excuse me, it's late, whether it's not equal to 0 or whether it's greater than 0 or whatever. It doesn't give you the standard deviation of x to calculate the standard error of b. So if they ask you specifically for the standard error of b, because remember, we already got the t values, so we already have what we need for that equation. But if we don't, or if they want it, then we're going to have to run one var stats in L1 to get the standard deviation in x. So we can calculate that SE, which is the S value. It's going to be this S value divided by this times the square root of 19 minus 1. But we don't need to have that. We do need to write the equation down low. We need to show that we're using our value minus the hypothesized value divided by the standard deviation to get a t value of negative 3.62. So now we're ready to take that t value and put it into the t distribution to see what the probability of being as or more extreme of that t value. So since it's a two-tailed test, we're going to double the probability that a t with 18 degrees of freedom is less than negative 3.62. If this would have been positive 3.62, we would have done greater than. But we're going to double that, so we get a p-value of 0.0020, which is the p-value. You can either show this with a curve, and if you want, you can show that, or you can show it with this probability statement here, but you have to link it to the probability. Since the p-value is equal to 0.002, which is less than 0.05, we reject the null hypothesis, and now we make our statement. There is sufficient statistical evidence to suggest that the slope of the regression line, now remember I had said we had to restate the relationship we're trying to get at, slope of the regression line relating average calories consumed by a toddler at lunch to the average amount of time he or she spends at the lunch table is not 0. And then I said, if it's a 0 or not case, it's nice to say whether there's a correlation or not. Evidence supports that a correlation exists. So in summary, the sampling distribution of B is predictable, allowing us, as long as the conditions are met, allowing us to perform confidence intervals or construct confidence intervals and perform significance tests. The population standard deviations are unknown, which makes we have to go to a t-distribution. You're going to require a bunch of plots for these to do your justifications of the conditions. The AP test is going to give you Minitab outputs and give you graphs most of the time. And so you can just reference those. If they don't, make sure you're always making copies. You can't reference a graph that you haven't shown. Two-tailed test at alpha is the same as 100 minus alpha percent confidence interval. So that means that 5% alpha level of 5% is the same essentially as a 95% confidence interval. If you would construct a 95% confidence interval and 0 is not in your interval, then you would say that the slope is not 0. You're 95% sure that the slope is not 0. That's the same as rejecting the null hypothesis. If 0 is included in your confidence interval, we would have done if we would have done a test instead, we would have rejected that b was equal to 0. So again, that's a two-tailed test, and these is the same as a confidence interval. All right, that's it. Good luck.